Okay, hopefully everybody can hear me. As Kirsten said, my name is Scott Yeager. I'm president of FAST International. Go to the next slide, please. I think they know what we're presenting. I have over 40 years of filtration. Unfortunately, I'm probably approaching 50. And over 20 of them involved Electrocoat Paint. I've had many senior level positions in all parts of management of companies in the filtration industry, mostly in the membrane air technology area. And FAST International, FAST has been in existence since 2004. Next, please. Okay, since the commercialization of E-coat, ultrafiltration has been a key process and is really there to ensure the consistency of the coating. Some of the earlier filtration processes were done using hollow fibers. Some of you may be around long enough to remember that. There's still some being used, mostly in Japan. And then the next systems that were taken into account were tubular systems. Both of those were both feed and bleed systems. And they have been almost completely replaced now by spiral element because they are more efficient with lower energy consumption. Next, please. This webinar will focus on applications of the spiral element design, since that's the vast majority of the types of systems and the types of ultrafiltration elements that are being used. We'll talk about the principles of cross-flow filtration, bag filtration, ultrafiltration element selection, how to correctly install or remove and install E-coat elements, systems design considerations, operating parameters, and probably the most interesting part of it is the troubleshooting area. Next, please. Without the application of cross-flow filtration, sometimes also called tangential flow, so you have TFF and CFF filtration, the ultrafiltration of E-coat paint would not be economically feasible. In fact, the filters would be plugged within minutes, if not seconds. In cross-flow filtration, there are three phases to the fluid path. The feed fluid path, which is the electrical paint that comes into the element, flows across the membrane, and with that flowing across the membrane keeps the membrane from fouling. Therefore, it lasts more than minutes, in fact, years. Then you have the retentate fluid path, which is the outlet of the filter of the paint. That comes out of the spiral element as a more concentrated form of particles, resin, etc. And then you have the permeate flow path, which is the relatively clean fluid that is filtered by the membrane. It consists mostly of water with some low molecular weight paint resins, typically in the neighborhood of 0.5% or less. And the permeate flow rate, the amount of water that goes through the membrane, is determined by what is called as the transmembrane pressure, or TMP. Next, please. We went back a ways. It's going forward on its own. Kirsten. Not too far. Next slide. Okay. Cross-flow terminology, cross-flow filtration. We talked about three flow paths. On the left, you'll see the feed flow path, which is controlled by the feed pressure. And on the right hand, you see the retentate flow path that is controlled by the retentate pressure. And we will refer to differential pressure, which is the difference between the feed pressure and the retentate pressure. And this what drives the flow of fluid through and across the membrane, not to the permeate side, but across the membrane. The transmembrane pressure, on the other hand, is what drives it through the membrane, which is basically the average pressure on the feed side of the membrane, feed retentate side. So you have the feed pressure and the concentrate pressure, or retentate pressure, divided by 2, minus the permeate pressure. That is what drives the permeate through the membrane. The feed pressure to the brake intake pressure drives the velocity across the membrane. Both of these are very important to the life and the performance of your filters. Next. Cross-hole filtration. It is a key factor in the life of the membrane. Without sufficient feed fluid velocity through the feed flow path, the membranes will follow. So we have to have a velocity of going across the membrane, which typically we look at between 7 and 10 feet per second, or 2.15 to 3 meters per second. That's the velocity that needs to be going across the membranes to keep them from following. This translates to a feed flow rate, which in opposite, not in opposite, but in addition to a velocity, is an indicator of the speed of which it's going across. And that's determined by the feed flow rate, and then it's calculated down by the feed flow path cross section. So you create the velocity. In most instances with ultrafiltration systems, you don't have any velocity measurements. And often you don't even have any feed flow measurements. So we'll often then recommend a feed flow rate per element that will translate with that feed flow path cross section to the feed flow velocities of that 7 to 10 feet per second, or 2.1 to 3 meters per second. It is dependent upon the diameter of the element, the feed flow spacer thickness, the open area of the feed flow spacer, and is not determined by the length of the element. That is independent of that. So you'll see an element like a 40281 have the same feed flow requirements as a 4040 element because it's not length dependent. Next. Next we'll talk about is the proper bag selection, pre-filtration selection. Bags are very important to the performance, particularly of spiral elements. The bags protect the spiral elements from having their feed flow ends or the feed flow spacer get plugged up with dirt that is in the feed paint tank that gets translated to the ultrafiltration system if it's not protected by a bag filter. So they're very important factors in the performance of the Electrocoat ultrafiltration system. In most industrial applications, there are primarily two different sizes bags being used. A number 1 size bag, which is a 7-inch diameter by 16-inch long, and a number 2 size bag, which is twice that, 7-inch diameter but 32 inches long. And the number of bags to be used is dependent upon the feed flow requirements of the ultrafiltration system, and that is to keep the membrane clean. So the feed flow requirements of the ultrafiltration system determine what is the bag configuration you're going to want to use, or the type of bag you're going to want to use as a pre-filter. Typically, a number 1 size bag should have a maximum feed flow of about 40 gallons a minute, and a number of 2 size, twice that of 80 gallons a minute. We always recommend that we use an extra bag more than what is required by the feed system in order to be able to shut down and change the bags without having to shut down the total system. So if you require 3 number 2 size bags, we would recommend for a particular desired feed flow, we'd recommend that you use 4 of the bags. Next slide, please, Kirsten. Also, bag filters come in different size housings, from a single bag housing to multiple bag housings. Most industrial applications or the custom coater applications use single bag housings that are in parallel manifolds so that they can be changed individually. Some of the larger systems, such as automotive assembly plants or large tanks, will use multiple bag housings. So multiple bags in individual housings. They'll also be sometimes connected either individually or in parallel. One of the things we should have in our housings is an inlet and outlet pressure gauge that has isolation to it. Paint loves to plug pressure gauges. So it's a good way not to have a pressure gauge operate is not to have an isolation valve or an isolation method. You should have a drain port on the bottom with a valve, vent pressure port with a valve on top of the housing, and the vent pressure port on top of the housing is used to push the paint out of the housing through the drain port prior to changing bags. We recommend bag housing should be 304 stainless steel. And one of the most important things that's often overlooked is that there has to be an adequate sealing method to ensure that the bag is sealed to the basket and the basket is sealed to the housing. I have gone into many plants that they've had problems with life of the spiral element. And when you open the element up and take a look at the bottom of the element is just covered with all sorts of big chunks of paint. And you say, well, how can that big chunks of paint that are inches, tenths of inches in size get through a 50 micron filter bag? And when you open up the bag housing, there is no adequate seal, or the seal is being bypassed between the bag, the basket, and the housing. So that's a very important thing. Most common style of housing that we see in the E-coat market for a single element is a side in, side out. And for a multi-element bag housing, it's a bottom in, bottom out. There are all sorts of other configurations, and really it doesn't make a lot of difference as long as your system is designed properly which one you choose. Next slide, please. How do we choose a bag filter? Most of the bags used in Electrocoat Paint are polypropylene needle felt that have been glazed. Glazing is a process where they heat the fibers on the outside of the bag so that they are fused together and then won't shed. Because a needle felt is basically a staple fiber, which is a short length of fiber that is entangled with one another but can come off and shed and possibly cause problems. By glazing prevents that. Typically, the most commonly used bags in the E-coat market are 25 to 50 microns. We've seen tighter ones, we've seen more open ones. We typically don't like to see more open ones. And the tighter ones only in conditions where you have a fine particulate that's causing a problem going through the bag. One of the things to comment about a bag filter, the micron ratings are a bit overstated. In other words, a 25 micron bag is probably closer to a 50 micron retention and a 50 micron to 100. That's one of the reasons I don't like to see 100 micron bags being used, because they are closer to 200 and they're too open for that. We also recommend using a welded seam versus a sewn seam. And the reason for that is that the needle holes put into the bag by sewing it are 200 microns in size. And so we have a 50 micron or 25 micron bag with a bunch of 200 micron needle holes. The second thing is, in my experience, one of the sources of potential silicone type contamination has come from the threads they use to sew the bags. We also recommend that the bags have a top sealed molded ring and not just a snap-in ring or a steel ring that's sewn into the top of the bag. And this will help prevent bypass of that of the paint around the ring. Recently I was at a facility that the bags had metal rings in it, and when you put the bag into the bag housing, the rings broke. They broke at the weld. And that's one of the things that we see a lot in the E-coat market is the users have a tendency, whether it's purchasing department or wherever it might be, to buy bags based upon solely on price. But a low-priced bag, if it's not a properly designed bag and sealed and welded bag, can cause the loss of thousands of dollars worth of ultrafiltration elements because of how they're made and how they seal. Next slide, please. Bag filter operation. The best thing to do is always remember to keep an eye on the pressure gauges on the bag filters, the individual bag filters, not necessarily one at the beginning and one at the end of the bag filter manifold. And that should be no more than 5 psi differential. That is the difference between the inlet pressure minus the outlet pressure. Why does this help? Well, one of the things we've seen quite frequently is when we open up an ultrafiltration element and look at the bottom of the element where the feed flow comes in, you'll often see hunks or big chunks of a gelatinous material, this gooey, it's like snot. It's most likely resin that has been come together into a large mass. And that's, you know, the size of it is sometimes a quarter an inch or more in size. That should not be coming through a 50 or 25 micron bag. But because it's viscous, it can, in fact, extrude through the bags. The other thing to warn is if you don't take particular care of, is that these bag filters will rupture at around 30 to 35 psi. Typically, if you're doing it at 5, you don't have to worry about that. But we've seen instances where people have done things like, do power wash their tanks, and then smartly they say, well, put it through the bag filter, but not the ultrafilter. And if they're not careful, those bag filters will build up differential pressure very quickly and rupture, and then it goes through the bag easily. How to change a bag filter? It seems pretty evident. Doesn't seem that difficult, but we've seen a lot of things done that were inappropriate. Of course, what you want to do is close the feed and filtrate valves off the manifolds, open the drain valve, and then pressurize the vent pressure valve to be able to push the paint out of the housings. We've seen it where a lot of times people don't want to wait for all of the paint to get out of the housings, and they'll stop it before the paint is all out, and they'll open the housing, and then they'll try to squeeze out the remaining paint. And in one instance, we saw that not only did they try to squeeze out the remaining paint through the bag, but after a while, they just turned the bag upside down and dumped the bag paint into the clean side of the bag filter. So you took all the dirt that was in the paint in the bag and dumped it back into the clean side of the bag filter, contaminated the system. By the way, that plugged up the ultrafiltration housings very quickly. Remove the bag and replace it with a new bag. Obviously, I always like to take a look at what's inside the bag. What do I see that's happening in there that should not be there? Is there large paint particles? Is there other things in there that should not be there? Is the bag showing indications that a high pressure or has been ripped? And it gives you a little bit of input as to what's happening in the paint. Make sure all the seals are clean, not damaged, and they're properly reset. Tighten housing by tightening the bolts, and do it, cross tightening as you would do like a tire on a car. Close your drain and vent valves, open your feed and filtrate valves, filling the housing full of paint. And then I'd recommend using the vent valve without the pressure, air pressure on it, the vent valve open the vent valve so that you get the air out of the housing. Next slide, please. Let's get into the spiral elements now, the ultrafiltration elements. Let's quickly discuss what is, in fact, in a spiral element. The membrane spiral element is composed of leaves, referred to as leaves. A leaf is a permeate carrier sandwiched between two layers of membrane, with a feed spacer placed between the membrane leaves. These membranes are then glued to the permeate carrier using an epoxy or urethane glue. A permeate tube, which is usually a plastic PVC tube that has 4 holes drilled around its circumference, that is used to transport the permeate from the carrier into the permeate tube. The leaves are all glued to the permeate tube to make a seal. There is an anti-telescoping device, or an ATD, affixed to each end of the permeate tube with a brine seal groove in that ATD. Now there's 2 ways of wrapping it or finishing it. One is with the fiberglass reinforced plastic. that is wrapped around it, or a netted wrap. Those are often referred to as low flows or high flows, respectively. And then on the ATDs, there's either one or two brine seals, and there's usually permeate O-ring seals that are supplied to replace the ones that are currently in the top cap and bottom plug. Next. Here's an example of a spiral element, and you can see the various components: the membrane, the permeate carrier, permeate collection material, the other membrane that the permeate carrier or permeate collection material is sandwiched between. And again, those two membranes are glued to that permeate carrier around each side and around the end, around three sides, so that the side that's facing the inside of the element is open, but all other three sides are sealed. And then there is the feed channel spacer that is placed on each side of that leaf. It is rolled up in a spiral form, and the membrane is glued on both sides to the permeate tube that has holes drilled in it, so that the fluid goes in across the feed spacer parallel to it in cross flow to the membrane. Some of the fluid goes through the membrane and goes into the permeate collection material, which transmits down to the left into the permeate tube. At the far end of the element, you see the parts of the anti-telescoping device, and then those are all hard wrapped or netted into an element. That is how it's constructed. It's a little bit more difficult than that when you actually do it, but that's how the whole thing. And those leaves are anyways from one leaf per element on a very small element like 1812 size elements to 12 to 15 leaves per element on larger elements like a 7640 or 8340 size element. Next slide, please. In the element selection category, pretty much everybody in the industry is currently using a PVDF membrane that is 100,000 Dalton, and a Dalton is a measure of the molecular weight of the materials that it will reject. It's also referred to as nominal molecular weight cutoff. So if you translate that to microns, it's about a 0.02 micron size, pore size. That material has a feed spacer of a 31 polypropylene diamond style and a permeate carrier that is 11 mil tree-coat epoxy-coated polyester. Pretty much all of the manufacturers that I'm aware of manufacture the elements with those components. There are some manufacturers that manufacture it with a thicker feed carrier of around 40-45 mils. That is sometimes less potential for particulate fouling in that feed spacer, but it does reduce the membrane area and has the potential for a lower permeate rate. Typically, all of the seals that are used, the rubber seals that are used in this industry are EPDM, and that is the brine seals as well as the permeate seals. And the permeate seals on the element can be interior to the element or inside the permeate tube, or it can be exterior to the element where the seals are on the top cap or bottom cap, or the seals are on an extension of the element, I'm sorry, not on the top cap and bottom cap. So there's really three choices at this point in time. It is the size of the element to be used, the number of elements to be used, and whether you want to use a high or low flow element. Next. Size of the element. They're available in lots of different sizes, to the smallest, which is a 1812 or 1.8 inch diameter by 12 inches long, or by 107.40. It's actually, there was a mistype, it was 107.38, which is a 10.7 inch diameter by 38 inches long. And the selection is really dependent on what is the desired permeate rate. And the desired permeate rate is probably best determined by the paint supplier or the system designer. And that's the amount of permeate that's going to be required for the surface area that is on each rack that goes into the paint tank, and how many racks per minute are there going in, or how many minutes per rack in the paint tank, how long the paint tank is, the speed of the rack, and the coating thickness. Those are all things that go into a calculation that say you should have this much permeate coming out of your ultrafiltration elements. So rather than the user operating that, I would recommend that that be done by the paint supplier and the system designer, one or both. Most element manufacturers in their spec sheets provide a permeate rate that they would anticipate for clean, new paint, depending upon the size of the element. So you can usually find that in their specification sheet that says this size element will provide you X liters per minute or gallons per minute of permeate, and then you can use that to calculate what size and how many elements you're going to use. An example is a 7640, which is a very common element in the industry, a 7.6 diameter by 40 inches long, typically provides between 2.5 and 4 gallons per minute of permeate per element and requires 70 to 80 gallons per minute of feed flow. Some of the newer designed elements that are showing industrial promise out there have improved that flow rate to up to 3.5 to 5 gallons per minute at the same fluid flow rate, feed flow rate. Next, Kirsten. Number of elements. Of course, once you need the total permeate rate and know the amount of permeate per element, you can just calculate the number of elements you're going to need. In the first example here, we have 25 gallons a minute of desired permeate rate and a 3 gallon a minute permeate per element, where you need 8.33 7640 elements, which really translates to 9. You don't want to go back down, you always want to go slightly larger. Or at 2 gallons a minute for a 5640 element, you need 12.5 elements, or 13 overall. And we typically recommend to use the larger elements, as that will reduce the CapEx, which means you use less valves, you use less piping, less rotometers, lots of less of, because you're using fewer elements that can significantly reduce the cost of the system. The other criteria is, what do I do? Do I use a high flow or low flow element? I'd like to say for right now, most new systems are all using the low flow element. And it's somewhat contradictory, because a lot of people will think low flow means low permeate flow. And that's not really what it means. That high flow or low flow is referencing the feed flow rate that is required per element. The high flows were were the first style spiral element that was introduced to the e-coat market back in the 80s. And they had a netted outer wrap to allow some of the paint to bypass the feed spacer. This required more feed flow rate to get the same velocity through the feed flow spacer, which means you needed more pump. They can also be very difficult to get out of the housing because of the paint buildup in that netted process to the paint housing or the filter housing. Just to give you an example, a 7640 high flow element requires about 120 gallons a minute of feed flow per element, where a low flow element require only about 70 to 80 gallons per minute per element. So that's the type of pump difference you're going to have. The low flow has got a hard wrap on the outside and a brine seal to prevent bypass. It requires less feed flow, lower pump requirements, and are usually considerably easier to remove from the housing. This is the design we recommend in most cases. Kirsten, next slide, please. Correct ultrafiltration element removal. Element flushing. Flush that element. Get it out. Get the paint out of it. Get the water out of it. That's very important, both for the cleanliness of the process and the system. Isolate the housing. Make sure there's no residual pressure when you open up the housing. Next slide, please. Element disassembly is pretty self-explanatory here, and there's two different sizes. One where the PVC or the stainless steel housing is independent of the element itself. That's why I call it independent housing, so that the element is a separate assembly from the housing itself. And that takes a little bit different process than the type we'll talk about as well, which the housing and the element are all incorporated together. So first thing I do is remove the permeate exit assembly. Take the top and bottom cap off. Remove the top cap by pulling up and twisting the cap until it comes out. Sometimes the element comes with it. In that case, it's great. But when it starts to come out with the top cap, have someone grab a hold of the element because you don't want it slipping off later and falling back down. If the element and top cap do separate prior to coming out, there's an extractor that we have available that'll go in and seal on the inside or grab the inside of the perm tube that'll assist you in getting that out. And then I always like to inspect the housing, the element rather, to see what's happened to it. Was the brine seal split? And you can see that from the paint in the inside under the brine seal and the brine seal. Is there a lot of viscous or dirt or particles or hard particles on the feed side of the bag? It'll tell you a lot what's going on with the element in its system. Next. The integral housing, and that's where the housing and the element are all one. You have to remove not only the permeate assembly, but the Victaulic clamps on the tops and bottom caps. But often when you move the top cap, you also have to remove the Victaulic clamp that hooks it up to the retentate port. You often do not have to take the Victaulic clamp out from the bottom cap to the feed port. And you then take out that integral assembly as one piece. And again, inspect it for the types of contaminants, and it'll give you a lot of history of what's going on. Next slide, please. Element installation. Again, we have two different processes, one for the independent housing, and then later I will talk about one for the dependent housing. One of the things that's often forgotten is people do not clean adequately the seals that are on the bottom and top caps where the O-rings seal the elements of the housing. And this could be an area where you will get paint bypass later that'll cause you problems. And make sure the O-rings are not damaged, as there might have been something sharp in there to cut it. You wouldn't want that to happen with the new O-rings. Clean all the excessive paint from the housing where the brine seals are as well. If there's a lot of dirt in that in the bottom of the housing, if you can, vacuum clean it out. And then close the CIP valve and fill the housing with about 1/3 full of water, DIRO water. The reason for that is you want to cushion the element when you're installing it, so if it drops, it's not going to be broken. Wet the O-rings. Always wet O-rings prior to installation, and it's easy to solve if you twist and push it when you're doing it. And it's in the bottom plug as well as later on when you put the top cap on. And lower the element into the housing, allowing the water to buffer the speed until the brine seal reaches the top of the housing. Twist and lower the brine seal. Kirsten, can you put this on hold for a minute? All the way to the bottom, where it would seal with the Victaulic gasket if it's raised up a 1/4 inch or 1/2 inch or more. There is a receiver at the bottom end of the housing at the bottom cap that is a cup, and you may have the bottom plug sitting on top of that cup rather than in it, causing that. And then, of course, move the gasket and the clamp and install, and then reinstall permeate flow outlet. Next slide. For the integral housings, it's very similar. Clean and replace the O-rings in the bottom cap. Again, always wet the O-rings, insert them twisting to make sure you don't dislodge the O-rings from their grooves or cut damage the O-rings. Install the bottom clamp with nuts typically facing out on the bottom clamp. And then clean and replace the O-rings in the top cap. Again, position it so that the retentate port on the top cap is feeding the retentate header, is connected to it and aligned with it. Wet the O-rings, insert the body, twisting again, making sure you don't disrupt the O-rings, and install a permeate assembly. Next. System restart. One of the most important things that is sometimes overlooked is to flush the system with water. So we like to thoroughly rinse it together with water and see what the water flow rate is with the element in it. That is an indicator of whether or not the element is going to flow very well or not. If the rotometer is indicating that it is a low flow rate, and typically these rotometers should be pegged with water at the very top, or if the water is 50% below the flow meter's capacity, there's usually a wetting issue that needs to be corrected. And I recommend flushing for at least 10 minutes each. The reason for that is that all the elements have some sort of material in them to allow to wet, whether it's a glycerin coating, whether it's a wetted item that's got chemicals and glycerin in it. They all have something that, although I've heard no instances of it causing problems with the eco tank, it's best to get that out. Shut off the water and the feed valves, the CIP valves, open the retentate valves to the headers, and then open the retentate and valves at the feed to the headers, and open while closing the bypass valve. This forces the paint to be fed through the feed header across the membrane into the bypass or the retentate header, and you adjust those valves to get a differential pressure of 30, typically recommended with a 50 psi on the feed side and 20 psi in the retentate. And always do not exceed the maximum recommended by the manufacturer, which is typically in around the 70 psi range. One of the other things to make sure you don't do is to have a permeate pressure that is higher than the retentate pressure or the retentate pressure higher than the permeate pressure by 5 psi. You often don't have pressure gauges on the permeate, but you can calculate the pressure by determining the head height it is from the element to where the highest point of the permeate is going to be. And if it's 2.31 pounds per foot of PSI, is what it is. And then check for paint leakage. Check to see if there's low permeate flow. Check for air in the permeate. And then always don't get too excited if it doesn't happen right away, if there's an issue right away. But run it for several hours to see if these problems persist. And then we'll talk more about what happens if they do in the troubleshooting guide. Next. System design. We already know the numbers and size of the housings or the elements that we're going to use. We know the type of element that we're going to use. Then we have to decide what the housing's going to be made of, the design of it, the piping sizes, the bypass, single or dual, parallel designs. Most of these are done by the people who design the systems. But typically we use either Schedule 80 PVC or a Schedule 10 304 stainless steel, or sometimes a hybrid, where the headers are stainless steel and the housing bodies are PVC, and the permeate lines are PVC. Typically PV is slightly less expensive than stainless steel. It will last up to 20 years. But for all you that might have 20-year-old systems, that PVC is getting very brittle, and you could have problems with it. We like to use a tapered header design rather than a straight design where the header pipe is the same diameter from one end to the other. We like to change the diameter of the header pipe so that the velocity inside that pipe is more consistent as you pull paint out of the pipe from the earlier elements. And again, we always design that by calculating the velocity for each stage in the header. And then, of course, minimize dead legs. Next. We should always put a bypass on it that feeds the feed between the feed and the retentate to isolate the system without stopping the paint pump. Sometimes an older system, we're replacing them, we'll just take it after the bypass is already there and build a system from there. Whether we use a single row of a number of elements or do we use 2 parallel rows of elements will depend upon the footprint that's there. How big a space do we have? Do we have a long, narrow space or a short, fat space? So that's always in consideration. Do you want a CIP system or just to replace the elements that's fouled? That will depend greatly on the frequency of fouling, the cost of CIP, and its effectiveness of CIP cleaning. I believe most paint companies out there recommend that a flow meter, feed flow meter, be put onto it, that you're not just relying upon the differential pressure to be an indicator of the paint velocity. They can be fairly expensive, but in many cases they're worth it. Some people want cumulative permeate flow meters. There are digital. Most of the systems out there now in the marketplace are what I call dumb systems. Everything is manual, but digital technology is available depending upon your budget to do that. Next. Operating parameters is pretty simple. You want between 40 and 60 psi feed pressure, between 10 and 30 psi retentate pressure for a differential pressure of 30 psi. We do not recommend the restriction of the permeate valves. Some people for a while thought that they would get longer life if they restrict the permeate valves, but we've also seen a lot of instances where your permeate pressure gets too high and you don't know it because you have no pressure gauges on it. If you have a feed flow meter, operate it at the recommended flow rate. And one of the things, never shut the system down for more than an hour without flushing with RO and DI water. I know systems that have been shut down accidentally, power outages, etc. But if that happens, you've got to have a way to flush it. Otherwise, the paint will cause fouling in the system laying static. And if it's longer than 7 to 10 days, flush the system regularly to make sure that you're not having a bacteria or bioburden building up in those elements. Next slide. Troubleshooting. Startup leakers. 2 principal causes. One is a O-ring seal failure, and this could be from a cut O-ring. It could be for O-rings having not been put on properly or not been put on at all. Paint buildup in the O-rings so that there's a bypass, or just damage of any type. Best way to do that is go back in and inspect all the O-rings, clean the O-rings groove, make sure everything is in place where it should be. Replace the O-rings if you can, and then replace it all, put it back together again, and if hopefully it'll stop at that point in time. If the paint leakage is very minor, I've seen it where you could just barely see a discoloration in the permeate flow tube or the permeate rotometer. I've seen it where I've been able to reduce the permeate rate to about half of what it was or more. And that actually allows the paint to build up in that leak and stop it without having to take everything apart. Now, the other issue with startup leakers, it can be a membrane leak. There is an integrity test method that, as far as I know, of all manufacturers use to see if the element is integral, but it is not 100% effective. My experience is that, well, actually it was at that time, PTI Advanced Filtration, the old AMT product line. When we took it over, they had about a 3% leakage rate in the field. And by doing a better job of it, we got it down, not perfect, but around 0.5% difference of leakage into it. And first thing, of course, you do is do the corrective action for the O-ring failure. And if that doesn't work, there's not much you can do in the field but contact the manufacturer. And they will either instruct you to do an integrity test in the field or ask you to send it back typically to see what's wrong with it. And there is a reverse bubble test that allows us to determine what's wrong. Next. Low initial permeate rate. PVDF membranes are hydrophobic, and because of that, they have to have something in the membrane to allow them to wet. That's either a glycerin solution that's been added or they are already wet in the bag. But this isn't always 100% effective. And the easiest way to determine is what is the water permeate rates when you're flushing it with water. If it's, as I said earlier, half of what it should be or well below what you think it should be, then you have a wetting problem. And it is much more easy to correct it with water in the system than with paint. Flush it for a longer period of time. Let the pump heat the water up to make it more easy to wet. Run it at a higher water pressure to assist in the wetting. And if all that fails, you can go to a CIP process if it's available. And the CIP cleaners that are available in the marketplace have a surfactant in them that will help in the wetting. If by chance you seems to do well on that but still have a low paint rate, permeate rate, or you didn't flush it with water and didn't know that you had a low flow element and put it on paint, there's not a lot you can do. One of the only things that I know of is to go ahead again with the CIP cleaner to see if that will re-wet the membrane. And if none of these work, then contact your element manufacturer. Next. Short element life. This is the #1 complaint that we get from the users out there. The elements don't last like they should. And you know, what should an element last? Well, it really depends upon how well you're managing your system. We have customers out there that elements have been in there for 5 years without having to change them, and they're still running well. And we have other customers out there that in 3 months their elements fail. Typically, on average, you should be getting a year's life out of your elements. So what causes this? It's actually very unlikely that it is the element itself, its performance capability. It's usually related to operating conditions, paint conditions, or both. And we've seen hundreds of these types of different conditions that have caused it. What I recommend is that you get the membrane element supplier, the paint company together, and the people at the user, and go through all of the various pieces of the puzzle. What is the differential pressure? What is it, which is the indication of cross flow rate? Were there any unscheduled shutdowns? Is there any bacteria issues? Have you experienced any high or low pH values? Any high temperatures that I forgot to put on it? We've had people dump the paste right into the weir without dilution, right where the feed to the ultrafiltration system was to foul the paints. Bactericide addition. Some people, when they add bactericide, will take the ultrafiltration elements offline. Some people do not. I've heard instances where that bactericide can have an effect upon element life. There's another area we'll talk about in just a minute about permeate foam that causes all sorts of issues. So the next slide, please. Permeate foam. We've had issues where, due to pump cavitation or the paint level was low in the tank, in the weir, to where the pump was sucking air into it and put a bunch of air in the feed flow, which translated into the permeate flow where you could see it. It was a foamy, bubbly mix. It can also be from a Venturi effect. Is there a small leak in the piping someplace where the velocity of the paint going through the pipe is sucking air into it as a Venturi. And this does cause quick permeate rate fouling. And in some cases, I've seen it reverse. We had one customer that I happened to be after in the install that we had this high foaming condition. And when we started it up, we were getting the expected flow rates in that particular element was around 5 to 5.5 gallons per minute. But within 1 hour, it was down to like 1 gallon a minute, and the foam was there. In that particular case, it was a low-level paint, plus the issue was that they changed the impeller on the vertical pump that fed the UF system, and it had a shorter shaft on it and raised the impeller higher in the paint, causing it to suck air. That particular case, once it was corrected, they were able to recover the permeate rate, which is great for the customer. Post-startup leakers. This is where you start out fine and run for a period of time, then all of a sudden you get high, it's a paint or smokers, as they call them, in the permeate rotometer. That is usually caused by a situation where the permeate pressure is either higher than or close to the retentate pressure, and is actually causing the paint to flow backwards from the permeate side rather into the paint side, and can delaminate the membrane. And then high paint solids, this can be caused by shear, heat, or whatever that may have lowered the molecular weight, allowing it to penetrate the membrane. And there are tighter membranes out there that can be used to correct it or to correct the membrane problem. Next slide. Let's go with the questions. I took a little bit longer. We started out a little bit later, but let's see what questions we can answer. And if not, we'll do it via email.
Okay, bear with me. I'm bringing my screen back up so I can see everybody. I have a couple questions. One is, what is the best way to help remove manufacturing oils that are already in the tank?
Best way to do that is with a polypropylene bag that is designed for oil removal. There's ones that are like a pillow that you put inside the bag housing that will absorb the oils out of the paint solution. Often is a drag-in from the cleaning process, that the degreasing process wasn't effective, and then subsequent rinsing processes got contaminated with oil, and then the parts drag in that oil into the paint tank. So it's best to take it back to where the oil problem is coming from, whether it's reducing the oil in the part, doing a better pre-clean degreasing, and make sure the pre-stages to the eco tank have oil removal capability in it, that's being taken out there rather than it gets into the paint tank.
Okay. John from Exalta just wanted to ask quickly if there was a presentation will be shared after the call. Yes, we will be sharing the presentation after the call. We will send the recording via email on Monday, and you will also have it on our YouTube channel. Bear with me as I'm getting these real quick. What is the molecular weight cutoff on fast membranes? Scott?
We have two membranes available. We have a 100,000 molecular weight cutoff membrane and a 50,000 molecular weight cutoff membrane. The 50,000 is a special membrane in that it has the same permeate rate as the 100,000, but we've used it in cases where there's been too much resin in the permeate, and we've reduced resin content by half or more by using that.
Why do bacteria could cause production problems?
Oh, bacteria is a killer for us. Bacteria do a number of things. One, the bacteria create a biofilm that is sort of like a slimy, greasy film that will coat the membranes and plug them up. The second is that bacteria like to eat the soluble acid, which in many cases is sulfamic acid, which helps the paint soluble. And when it eats the sulfamic acid, it produces another acid out of it, but it also increases the pH, where you don't normally want to operate between 5 and 5.5 pH. We've seen them operate up to 6 or more pH that way, which is going to cause paint instability, which follows the membranes.
I'm sorry, I misread that question a little bit. Why does bactericide cause production problems?
I think it's a combination. It increases the biofilm, and It's sort of anecdotes that I've seen from various customers, especially that surfactants can cause issues, and sometimes there's surfactants involved in it. But I've seen customers have complained that after they use a biocide to reduce their bacteria, if they leave their ultrafilters online, that their permeate rates go down. So they just bypass at that point in time the ultrafilters when they've had the biocide, and they seem happier with it.
Okay, one of the additional questions is FAST quotes 60 to 65 psi as max inlet feed pressure. Which is it?
I'd like to see 60 psi. The elements will take more than that. It's not necessarily the element construction that's the issue. But once you start getting high feed pressures and you maintain your 30 psi differential pressure, let's say you have 70 psi feed pressure, then you'd have 40 psi differential pressure. And then your transmembrane pressure is a lot higher. That could create a compaction of the dirt on the membrane because you've got higher transmembrane pressures that will cause what is called concentration polarization, where the material on the membrane surface gets compacted and reduces flux.
Okay, Paul mentions our literature quotes both the 60 and the 65 as maximum. I will, Paul, look into that and double check our literature. One of the other question is, on one of the slides you mentioned about mil, MIL. What unit is this?
That's thousandths of an inch.
Okay. Another question is, when would the best time to replace an older system?
Now. We got some available now. At around 15 years, you can see problems with the PVC getting very brittle. Valves start breaking, and it starts causing more problems in operation. You know, how many systems have I seen where there are 4-element system, there's only 3 on there because the other one's busted, it was broken, the piping is broken, or the CIP piping is broken. So at about 15 years, you're getting pretty much your life out of that system. And that's also going to be dependent on the temperature that's operating under, how many cleaning cycles has it gone through, all that things. But, you know, 20 years is about the max I'd like to see it. PVC.
Okay. And as of right now, I think I only have one last question, and that is, one last question, and that is, double or single seal at top, double for back flushing. I'm not sure if that's a question or just a statement, or that was from Paul. Paul, if you could elaborate what you're thinking, or are you good, Scott?
I'm good. Some elements come with 2 brine seals on it so that you have one that prevents the paint bypass. But when you do a reverse CIP, and that reverse means doing the CIP from the retentate side to the feed side, it locks and seals that up so that you flow backwards. It's not a bad idea. It's principally to remove the big particles that have accumulated on the bottom of the filter element, which shouldn't be there. If you have a 50 micron effective bag filter, you shouldn't have that issue. But it can happen. And the reverse brine seal backflush capability makes sense.
Okay, cool. I think I have one last question, is that when would you recommend using a thicker feed spacer membrane for a UF filter?
If you're having a lot of problems with thick viscous materials building up on the feed end of your filter, then I would look at going with a thicker brine seal. As I say, the downside of that is you're going to have less membrane area, which is going to affect your permeate rate. The best solution is, of course, control your paint conditions so that you don't have this viscous material building up that is also going to cause issues with your coating.
Okay. Well, I think this is the end of our webinar. I don't have any more questions. Thank you again, everyone, for coming and for listening to Scott and dealing with our technical troubles at the beginning. This is our first webinar, so the next one should be a little bit smoother. The recording will be sent out on Monday and on our YouTube channel, and it will be on our new website, which is going to launch in either next week or the following. We will send that survey, so you can please give us feedback and any questions and any ideas for future surveys.